Welcome back to part 2 of the video series dedicated towards our understanding of balance and stability. In this particular video section, we'll be looking at the variables that tend to affect the balance and stability of a particular object. We've highlighted what those variables are in the previous video, namely what the position of the line of gravity is relative to the base of support. So this object will have a center of mass, meaning that gravity will act through it. What is the distance of that line of gravity relative to the base of support? That also takes into consideration what the area of the base of support is. How large is it? Is it quite a significant distance, or is it rather small? What is the mass of the particular object, and how does that affect its stability? And also the height of the center of gravity relative to the base of support. Not only how far it is from either end, but also how high it tends to be relative to the base of support. So we'll unpack each of those in turn. The one that I want to start with is looking at the role of mass. Okay, let's say, for example, I were to apply an upwards force on the very end of this particular block. You would agree from previous videos that that would cause a rotation of this block in a anti-clockwise direction, right? If I apply a force, it's going to start rotating. What happens to this block ultimately, in other words, whether it continues to topple over or whether it tends to return to its initial equilibrium position, is dependent on, like we said, where that center of mass is located relative to the base of support, so on and so forth. For now, we want to investigate the role of mass of this particular object. How difficult is it to start rotating it? Okay, so if I were to apply an upwards directed force on the very edge over here, this is the force of me pushing, right? Then this would tend to cause that rotation. We know that there is another force acting on this, which is gravity, which tends to act through the center of mass of this particular object. So here's the center of mass, and we've got this downwards directed force of gravity acting on this particular object. Okay, both of these forces are a given distance from the axis of rotation. So if we assume that there's a pivot point over here, then the magnitude of the torque forces are going to be dependent on how far they are from this axis of rotation. So say, for example, that this force of gravity, if I take this length down here, I'll just call it L, I'll say that the force that I'm pushing is being exerted a distance L from the axis of rotation. It's just the length of that object, right? It might make it a little bit easier to understand. And this force of gravity is exactly half of that L distance. So that distance over here is just going to be L over 2. Okay, so we know that this force of me pushing is going to cause an anti-clockwise rotation. We know that this force of gravity is going to be causing a clockwise rotation. And under equilibrium conditions, we know that the sum of moments equals 0. So in other words, what that's saying is maybe I was pushing just hard enough to kind of counter this force of gravity, that this block still won't move, but there's not going to be it's not going to be entirely touching this surface, so there's no normal force acting upwards on this particular block at this point in time. It's only these two forces acting on it. Okay, so that means that the sum of all moments, or the sum of all torques, has to equal 0. Well, the torque that I create by pushing on the very end here is equal to, we'll just call it the force of me pushing multiplied by the distance from the axis of rotation which I tend to push, which is L, minus the force of gravity. Let me just keep these colors a little bit more. Force of gravity times the distance that it is from the axis of rotation, which we said was this kind of L over 2. And all of that has to equal 0. So there's just one more thing that I want to substitute in that. We know that the force of gravity acting through the center of mass of the object is just equal to the mass of the object times the gravitational acceleration, right? So I'm just going to replace that in our particular scenario over here. So I have the force with which I pull multiplied by the distance at which I'm pulling, minus, and then I have this mg times L over 2, and all of that has to equal 0, right, if I'm kind of just keeping it where it is. Alright, so if I take this to the other side now, I have this scenario where it's the force of me pushing multiplied by the length is equal to this mg L over 2. So how much force do I have to push with in order to keep this equilibrium situation true? Well, I'll divide everything by this L component. So the L's will cancel out on either side, and I'm just left with mg over 2. Okay, so in other words, the force that I have to apply is equal to half the weight of this particular object. Remember, mg over here is the force of gravity acting on that, which is just equal to the weight of the particular object. Okay, so the force that I have to apply is half the weight of this object in order to keep this equilibrium condition. Like I said, I want to investigate the effect of mass. So let's say if I keep everything the same, all these distances the same, the force of gravity doesn't change, the distance that I apply the force and the distance that the gravitational force is acting relative to the axis of rotation is the same. All I'm manipulating is the mass of the object, and what I'm going to do is double the mass of this object. So how is the force that I have to apply compared to this second scenario? So in scenario 2, if this was initially just m, now I'm doing 2m, double the mass. So I'm just going to rewrite this over here. I'm still applying the same force, and it's at the same distance, so the torque that I apply is going to be the same, right? Minus this force of gravity times the distance that it is acting from the axis of rotation, and all of that is going to still equal 0. Note, however, now that Fg, hang on, let me just get this color right here, that Fg is equal to 2mg, right? I've doubled the mass, so the weight of that particular object now is equal to 2mg. So that's all I'm going to replace within this formula over here. So it's still going to be the force of me pushing times the distance that I tend to push, minus, we'll use that new convention here, this 2mg times L over 2, and all of that equals 0. Okay, so just bear with me, I'm still going to do this step by step. So if P, the force that I have to apply, times the distance that I have to apply it from, remember I'm going to take this over to the other side now, is equal to 2mg times L over 2. Note that the 2's here cancel, so it's just this FPL is equal to mgl. So let me just write that out to make sure that there's no confusion. FPL is equal to mgl. So if I want to find out how much force I have to apply, divide through by L on both sides. So that's just going to leave me with the force that I have to apply is now equal to mg. Notice that when the mass doubled, now the force that I have to apply is equal to the mass or the weight of the object, right? So the force that I have to apply is equal to the weight of the object when the mass has doubled. In the initial scenario, the force that I had to apply was equal to half the weight of the particular object. Okay, so if I had to kind of compare, if this was the force that I had to apply in scenario 2, and this over here is the force that I had to apply, let's give me a red color, this was the force that I had to apply in scenario 1. How much more force did I have to apply in scenario 2 relative to the force that I had to apply in scenario 1? So just for sake of brevity, I'm just going to call this FP2. How much more did I have to apply? So we make this a ratio. relative to the force that I had to apply in scenario 1, so FP1, well, that's equal to just this mass times gravity. That's how much force I had to apply in scenario 2 relative to this mg over 2. Well, if I have something divided by a ratio of something, then I can multiply it by the inverse of that. So that's just going to be, I'm just going to do it down here, mg multiplied by the inverse of this, 2 over mg. So notice now that the mg's would cancel and I'm just left with 2. So in other words, what that's saying is that the force that I had to apply in scenario 2 relative to the force that I had to apply in scenario 1 is twice as big. Right? I had to exert twice the amount of force in the second scenario than I did in the first. And the reason that is twice as big is because the mass was twice as large. So we could see that the force that I had to apply in order to initiate a rotation is proportional to the weight of the object. So when the weight tends to increase, the force that I have to apply tends to increase, right? So the stability of this object, or how difficult it is to move and rotate, is directly proportional to how much it tends to weigh. Okay, so that's the first part. I will subdivide this video into all the different components. I don't expect you guys to know all these formulas. I just expect you to get some kind of intuition as to why something is more stable when it is heavier, or what the base of support has to do with its stability, or the height of the center of gravity, and so on and so forth. So this is the second set of videos, but I'll subdivide this into smaller chunks just to make it a little bit more manageable as well. Okay, so in the next video, we will look at the height of the center of mass and what role that has on its stability.